Great. Mike Perry from Largo Clean Energy giving an update on the densification and gel formation work. So take it away, Mike.
Okay.
Can you hear me now?
There you are, Natalia.
Okay.
Yes.
I'm sorry. I'm very sorry for it. I have just a new laptop.
No problem, Natalia. We'll let Mike finish up here, then we'll come right back to you.
Yes. Thank you.
Go ahead, Mike.
So this is 5 different production processes that we're working on in partnership with the Manufacturing Office Award to work on stack production processes and electrolyte production processes. This is obviously talking about one of the electrolyte production processes. We are going to get over $4 million from DOE to support the work on these 5 different processes. But I'll just talk about this one today. So next slide, please. Go on. Next slide, please. So just the problem statement, what are we trying to fix here? We all know on this call that VRFBs are the most mature type of flow battery technology. But with VRFBs, we actually have quite a bit of cost associated with just getting the electrolyte on site and in the tanks and ready to go. And what I mean by that is basically we're shipping a lot of water because, we have like 1.45 molar or thereabouts vanadium in an aqueous solution, a sulfuric acid-based solution. And then typically, unless you have a very small system, you can't really ship these tanks full of this heavy electrolyte because it exceeds the weight limits, plus it's sloshing around because it's a liquid. And it is, considered a hazardous chemical to be shipping around. So it's challenging. And so if you're doing megawatt scale systems, you end up shipping the tanks empty or building them on sites. And if you're shipping tanks empty, you're really paying to ship air, which is kind of wasteful too. So the cost of just, logistics here is higher than we'd like. And obviously capital cost is what we're trying to focus on bringing down. Next slide, please. So the concept that we worked on here, or still working on, is to make a gel by first densifying the electrolyte, making it basically precipitate out in an expedient manner, and then having this gel is semi-solid, or it really is a solid, at a much lower weight because it's higher density, be able to be shipped inside the tanks. So some people sometimes ask, why don't we just make the electrolyte on site? And, because we have solid powders like vanadium oxides, but the mixing process is more than just mixing. It's a chemical conversion. You're converting vanadium oxides, which are not soluble in aqueous solutions really, to vanadium sulfates. So you're doing this reaction as well as mixing acid and water, which you obviously have to do very carefully whenever you do that. And these electrolytes are typically made today in a factory in glass-lined reactors because they can withstand the temperature and the caustic nature of the sulfuric acid solutions that we're playing around with here. So that mixing process does not bode well for something on site. We want something very simple on site. So that's why we came up with this concept, which is first densify it, precipitate it, ship it in the gel format, and then just add deionized water on site. That's all you have to do. But the challenge here is that these precipitation reactions, even at high concentrations after you densify it, can take very long, like, more than 24 hours in some cases. So we wanted to make that much faster. And I had noticed some work done by the University of Kansas, cited here at the bottom, where they're trying to make a 2-phase vanadium battery with hydrogen. And they were using nucleation materials to accelerate the precipitation. And so I thought, well, this is a way we could accelerate the precipitation for this purpose as well. So we collaborated with the University of Kansas to do the lab work that I'll show you here briefly. So next slide, please. So first we want to densify it. Now, obviously, you could just make a very concentrated electrolyte. That's an obvious way to go. Or you can take a regular electrolyte, which we did in this project. And so we shipped Kansas our electrolyte, which is close to a 1.5, 1.6 molar vanadium solution. Notice it's V3, V4. This is really what you use to start the battery, right? What we commission the battery with is only the 3 and 4 oxidation states, and then we do a formation charge. So we're just playing around with 3 and 4 here. But the densification process that Kansas used was actually something you could use at scale too, I believe, which is it's called forward osmosis. And so you expose the solution to a more concentrated draw solution, which in this case was concentrated sulfuric acid, which is what we use to make the electrolyte. So you can see how you could integrate this into a mixing process in combination with the densification process, if you'd like. And what that does is, by osmotic pressure, it draws the water out of the vanadium electrolyte, and we're able to densify it to something like shown on the right there, like half the volume or even less, very quickly. In fact, what Kansas was using for the osmotic cell here was just a vanadium flow battery cell, because the Nafion-like membranes that we use are good osmotic membranes. So you can actually just use a cell to do it. And all this work that I'm going to show you that we did at Kansas, we recently published in a peer-reviewed journal article, which you can see here. And if you're more interested in the details than I can do in this presentation, please refer to that publication. Next slide, please. So, when you densify, you make them oversaturated, and I'm not going to go into the details, but basically we are heavily oversaturated, but it will still take a long time to precipitate these things unless you add nucleation materials. And that's what Kansas has already discovered, some nucleation materials, which include things like carbon. Carbon electrodes are nucleation materials for the precipitation, which maybe isn't good. But the other interesting thing is that when you make these precipitates with the nucleation materials, you make low crystallinity solids, which are different than what you'd get normally. And those low crystallinity solids also serve as nucleation materials. So you don't have to add a foreign material to promote this accelerated precipitation, which I'll show you. So next slide, please. So we explored the effect of adding these nucleation materials and the effect of densification, meaning how much water did we take out of the electrolyte. And here we show some results for 60% densified electrolyte, meaning, we took out like 40% of the water, thereabouts. And then we add various amounts of this nucleation material, which really is just a low crystallinity salt that we've already made somewhere else using a different nucleation material like carbon. And then we also explored the effect of mixing. And it turns out that you have to have some mixing, you have to have some nucleation materials to get what we want, which is case B. And you can see in case B that the beaker is actually turned upside down in that picture after just a relatively short exposure time, because we've made a gel. That gel is a solid. It doesn't come out of the beaker. We made a solid in a longer periods with the other case A and case C, but you can see it's very different solid. These are the highly crystalline salts that take longer to form. They're also harder to dissolve, whereas the gel is a low crystallinity form, so it's not as low an energy state, and therefore it's easier to precipitate and it's easier to dissolve. Next slide, please. So we actually explored quite a few variables really to try to get the parameters we needed to scale this process up to larger scale. This is all benchtop lab work. We did it at different volumes, not shown here, but we also explored those key parameters I just mentioned, like the nucleation density, how many milligrams per milliliter of the nucleation material do we have, how long do we mix? And then we showed that, if we have a long enough mixing time and enough nucleation materials, like on the right-hand side, you'll get full gels in a reasonable amount of time. So we really have achieved what we wanted to do at the lab scale. We've shown that this works. We've actually collected the parameters, which I don't have time to go into, what we need to scale this up. And now we need to scale this up to a prototype system, which is what we're going to work on next. Next slide, please. The other thing I do want to mention is I mentioned like these low crystallinity salts, they will dissolve very easily. So you can see on the top, we take the low crystallinity gel-like solids, we add a little water, and within less than a minute, they're already redissolved because again, they're not high, very low energy, high crystallinity salts. They're more, amorphous, if you will, and so they dissolve readily. Whereas the crystalline solids, you can see even after, many minutes, it takes over an hour to get them to dissolve again. So this will make it easier in the field when we bring out these gels and when we add DI water, it will be easy to reconstitute the electrolyte. And that's the goal, right? To reconstitute the electrolyte just like it is today. In other words, this concept, we're not changing what we do in the battery. We're just changing how we make the electrolyte, ship the electrolyte, and then commission the battery. And that really reduces production costs, logistics costs, and I think it also enables us to have fewer electrolyte mixing production facilities to serve a large geographic area because we're shipping less weight. So I think next slide is sort of my summary in a graphical format, which is again from the paper that we just recently published, showing that we can ship something like half the volumes, and they probably can be shipped in the containers because the weight's low enough now to ship in a shipping container, which is what we use at Largo for our on-site storage in our batteries actually as containerized tanks. And next slide is more of a summary in words. So I showed you that we have shown what we can do this on a lab scale. It does look like there's no showstoppers here, at least at a lab scale. We've taken the measure the parameters we need to scale this up. Our next step will do this at a prototype scale, meaning like a short stack. We call it like a 20 cell stack. Type of size for us is pretty small, but just to show that we can do this more at many liters versus just the milliliters that we are doing here. And then if that works well, then I think we can talk about actually taking this to commercialization. And so I just want to acknowledge my collaborators at the University of Kansas, as well as the financial support from the U.S. Department of Energy. And with that, I'd love to take any questions you might have if we have time.
Thank you, Mike. Yeah, exciting developments, and look forward to seeing more from you. If anyone has any questions for Mike, if you put them into the Q&A, and Mike, if you could go in there and just answer questions directly, that would